Okay, so following up, let's look at this function more carefully now. So we see this is our electric field in the x direction as a function of x, but since the y component's cancelled out, as we previously verified, this is also our electric field as a function of x. So let's take a look at what the profile of this electric field looks like as a function of x along the x-axis on either side of our ring, meaning on the side of the ring where the x-axis is positive, on the side of the ring where the x-axis is negative. Okay, so let's take a look at that. So here we have this online graphing calculator, and you will see that on one end we just okay, now here you see that our electric field here as a function of x is standing here, and I decided to consider the charge a positive for the time being. Here's our constant k, 9 times 10 to the 9. You may argue, not exactly, 8.99 times 10 to the 9, but who cares? It's a very small difference. Now, we see over here in our graph that this is the center of the ring at x equals 0, and then as we go away from the ring, about the x-axis, we reach a maximum value for the electric field, and then it decreases. So the reason why we see all positive values for the electric field on this side is to indicate that the electric field is pointing in the positive x-axis along this side. Now, likewise, when you look at the negative x-axis, you see the electric field values are all negative. So you see over here that the electric field is pointing away from the ring in the negative x direction as well. Now, an interesting thing here to we can see from the graph is that these two inflection points, we see that the electric field does indeed have a maximum further away from the ring. Now, how does the radii affect this? So let's see. I set the radii to unity here to make it easy, but as I increase the radii, you see that maximum value on either end of the rings becomes less and less pronounced. We don't even notice it. We might even miss the fact that there is indeed a maximum value for the electric field on either side of the ring at a certain distinct location. So let me set this back equal to 1, and that was just the radii. Now let's look at our charge. Here, what happens if I change the magnitude of the charge? Just increases all the values of the electric field at any given point on the domain or the x-axis. So nothing special. What if the charge is negative? Doesn't change much. It just flips over, and we see on the positive x-axis the electric fields are negative, meaning the electric fields will point towards the ring. Likewise, on the negative x-axis, we see that the electric fields are all positive, so they're pointing towards the ring, towards the positive x-axis. So that's what we can take away from this. So let's go back and put everything in brief. Okay, so we saw our profiles kind of look like this. I'm not an artist, but I think you see the point. So this is when we consider our charge to be positive, but what happens to this graph when we consider the charge to be negative? It just flips over on us, and this is when the charge is negative. And we saw that everything works out fine when you look at the graph and what the results are and you plug in values. So we see over here, when the charge is positive, our electric field points that way. Now on either side of the ring, when the charge is negative, we see our electric field on either side of the ring points towards it. for when the charge is negative. So all of this makes sense. So we can even figure out what are those points along the x-axis for which the electric field is a maximum. Luckily, this is an invertible function. It is a continuous function. So we can go ahead and take its derivative, set it equal to 0 to determine the maximum value of the electric field and their respective locations. So we can determine these locations, or where these inflection points exist, by taking the derivative of our electric field and setting that equal to 0, because that's where the rate of change is 0. We're going from, if you look at the green over here, from an increasing, or rather from over here, we're going from an increasing function to a decreasing function across that point. So it works out. And that's how we can find our maximum value is equal to 0 at x, for x where, actually for Emax, our maximum electric field value. And just to clarify, the absolute value of that electric field vector, because remember, it also has a sign when you consider electric field, because it is a vector quantity. So that's just looking at this function in a meaningful way.